Hello, this is the first video on a series about the nature of musical dissonance, in which I will try to popularize recent scientific progress on the nature of dissonance in music. Before we can start, I would like to go through really briefly about some basic notions about sound, and today I would like to talk about pure tone and sine waves. So, the most basic musical sound that you can have is pure tone or a sine wave. And this is how it sounds, and this is how it looks. The very familiar shape of wave. So it has two properties. The first one is frequency, which is the number of repeats per second. So again, if I play this A, we can see on oscilloscope that it has a certain amount of repeats per second in this screen. If I increase frequency, first of all, we hear higher note, and second thing, we see that the graph became kind of squished and there are more repeats fitting in this screen. So again, higher frequencies mean higher notes, so that's simple. So another property is amplitude, which is the difference between highest peak and lowest valley. So, and a lot of the time people think that this is the most trivial property, but actually there is a very interesting thing about it. A lot of people think that amplitude and loudness is the same thing, because, like we all know it, it's obvious that if you play something with that amplitude, it is that loud, then we reduce amplitude and it kind of goes away, it is less loud. Then again, if we restore it, it is loud again. So that's why a lot of people think that amplitude is loudness, but actually it's not true. Because amplitude, it is a physical property of waves, you know, it's something that you can measure, something that it is objective. Loudness is a human being perception of sound pressure. It is a subjective thing. And our auditory system, the way we hear sounds, actually have a lot of very interesting properties that are not self-evident to us. For example, loudness is not only dependent on amplitude, but also on frequency and on duration of the sound. What do I mean by loudness dependent on frequency? Well, know that people hear frequencies from 20 Hz to 20,000 Hz or to 20 kilohertz. And the further you go into higher frequencies, the less audible they are. So if I play a really high note, you know, that's a really high note, maybe a bit lower. No. Like this. It's not very pleasant, but it's not very loud. If I play something here, it seems a bit louder, right? But on oscilloscope you can see it is the same exact amplitude. And it's just because we perceive higher frequencies not as good as we perceive mid-range. And this phenomenon is usually explained when people explain what is curves of equal loudness or Fletcher Munson curves. So let me tell you how to read those curves. So the first thing is that we see a number of solid black curves on this graph. Let's take and focus on the bottom one. So here, this curve represents, each point in this curve represents a point of equal loudness. What does it mean? If we decide to play a sine wave at 3000 Hz at this amplitude, in order for a lower sound, like let's say 300 Hz, to sound equally loud, we actually have to play it a little bit louder, with a bit higher amplitude. And that difference between tones, it's not constant with the overall loudness. So if we play this first tone louder, for example, with that loudness, actually we see that this difference diminishes. And the most flat part of and at 90 decibels we perceive the sound the flattest we can perceive sound, you know, like it's all frequencies are more or less the same. And that's why mastering engineers master their tracks at 90 decibels, at the loudness of 90 decibels, because this is where the sound, our perception is the most analytical, if you can say this. Okay, so that is with frequency. Another thing that impacts our perception of loudness is duration of the sound. So if the sound is very short, like 10 milliseconds, like a really quick snap of like say 120 decibels, you know, the pain limit, it's actually not a big deal. But if it is a constant 120 decibel hum, it is very loud. And actually, sounds above 300 milliseconds, they are kind of the same loudness. But the shorter than that, the shorter the sound is, the less loud it seemed to us. Okay, but coming back to pure tones. One pure tone corresponds to one note. So to note A, to note F, to any note you actually want. And if we play two notes sounding simultaneously, like say I play this A major third, this is called musical interval. And common musical intervals like major third, like fifth, like fourth, you know, they have specific ratio, they have specific frequencies that are fixed and that are all instruments are tuned to those frequencies. But actually, there is no reason for us to not to use some in-between notes or, you know, to tune our instruments a bit off if we prefer that kind of sound. There's really no rules. It's just kind of more or less tradition, you know? And in fact, in past, people were tuning instruments differently. Like ancient Greeks, they had completely different tunings, nothing like what we have now. So when I'll be talking about musical interval, I really mean any two simultaneously sounding musical notes. So that's it for today. I talk about everything I wanted. So in the next video, I'll be talking about the spectrums of real instruments. You know, what is spectrum? What are some imperfections maybe in real instruments? So until next time, goodbye.